for this example, the rope fixed to two walls.
Right.
Whatever the time may be, the position of these two particles is always 0.
Right.
So by applying these two boundary conditions, we get the frequencies as n by 2l into v, where v is the velocity. So we have different frequencies for n1, 2, 3, so on.
Right.
So for n1, it is called as fundamental mode.
Okay.
And each of these is called as harmonic.
Right.
This is first harmonic, second, third, and so on.
Right.
And then from this, if you remove the first, that is the fundamental mode.
Right.
1, 2, 3, you remove this.
Okay.
From here, it's called as overtone. This is the first overtone. This is the second overtone, and so on.
Right.
Like this terminology will be used for each and every case, and this will be very useful in the problems.
Right.
And then coming to sound. So the assumption which we take is propagation of sound in gas is adiabatic.
Okay, I'll just dwell on that. So basically at this stage of physics, when we model sound, we assume that the process is adiabatic. And what does actually an adiabatic process means? We'll go through it quickly.
Yeah.
So
there is no heat transfer.
Oh, exactly.
And applying that, we get this velocity as under root gamma RT by m.
Okay.
And from this we get the approximate value as something around 330 meters per second.
Right.
And that is what we use in most of the calculations.
Okay. Yeah, so that's another reminder that whenever velocity of sound is not given to you, assume it to be around 330. Okay.
And then since this is a sound wave, there are two things oscillating. One is the pressure and the other is the displacement. So we have two wave equations. The first for the displacement and the next for the pressure displacement.
Right. Both of them describe the same wave actually,
Yeah.
and either can be used depending on what we want
Exactly. To know. But the difference is the pressure lags the displacement function by a phase of pi by 2 radians.
Right.
That is why you have this minus sign and then this pi by 2.
Correct.
And there is a relation between the amplitude of displacement and the amplitude of this pressure.
Right.
That is given here, which is BAK. B is the bulk modulus, A is the amplitude, and K is the wave number.
Right. Which is 2 pi by lambda.
Yeah.
Okay.
And then we have seen progressive waves of sound, and even the stationary waves of sound are possible.
Right.
So what is this? What is a closed organ pipe?
Okay.
A pipe which is this way, and there is a facility to fill water from bottom.
Right.
And this length is adjustable.
So when we say there's a facility to fill water, we mean that sound will probably not go there.
Yeah.
Okay.
This end is treated as a displacement antinode.
Right.
Like the displacement of the particle at this point is 0.
Okay.
So, and when you apply the
In
boundary...
fact, that is a displacement node.
Yeah.
Okay.
And when you apply the boundary conditions on this, as you have done for the string question, you get the frequencies as 2n minus 1 into v by 4l.
Right.
Where n is 1, 2, so on.
And I guess most of you will have material which makes you familiar with the fact that in such an open pipe, you treat the bottom as a node and the top as an antinode. Okay.
Since this is the free end, you treat it as an antinode.
Right. So this, working along those lines, we arrive at these expressions.
Yeah.
Okay.
So some of the waveforms which you can see are like this. This
Correct.
is the fundamental mode, and then you get with one antinode and so on.
Right. Okay.
And similarly, there is an open organ pipe also.
Okay. Where both ends will be.
Yeah. Where both ends are open.
So we'll treat them
And
both
both
as
ends
antinodes.
have an antinode with one node at the middle.
Right.
And then again one more loop adds
Exactly.
to this and so on.
Okay.
Okay. Till now what we have seen is interference of waves with same frequency.
Right.
But in beats it is slightly different.
Okay.
There are two waves with nearly same frequency
Right.
traveling in same direction. This is the most important thing, which interfere at a point in space.
Okay.
So we take two waves. Suppose this is with let's say 7 hertz and then the other with say 14 hertz.
Right.
Now when these two interfere, you get a very different phenomena. You hear a waning and waxing of sound.
Right.
At some instance you hear a sound with very high amplitude or
Okay.
very high intensity.
Right.
And at sometimes with very low intensity. So let's consider point x equal to 0 because it happens at a point in space which varies with time.
Right.
So let's take these two. And when you use the principle of superposition, this is what you arrive at.
Correct.
And when you plot this graph, that is 2a cos so and so,
Right.
you get something of this kind.
Okay. Right.
So it is something like this.
Okay. So we are creating an envelope inside this. We
Yeah, exactly.
See that. Okay.
So, and then this is the envelope which I am creating.
Right. So an
And then-
envelope is like an artificial construct that we create to better show how the wave is behaving at that point.
Like inside this envelope, the amplitude is oscillating with a frequency of v1 minus v2 by 2.
Right.
And the wave on whole is traveling with a frequency of v1 plus v2 by 2.
Right. Both of these results come just simply from superposition, and you
Yeah.
can check that from the expression for y1 plus y2.
And in most of the questions, the question requires understanding the beat frequency,
Right.
which is nothing but the difference in frequencies of the input waves.
Correct. Okay, so
And-
we move on to probably the most important and the most well-known concept here, because this, I'll tell you this actually. We will see this right now mostly for sound, Doppler effect. But later, Doppler effect is there in so many forms, in so many kinds of physics, so many different aspects of physics, and this concept, of something which is related to other things like frequency changing due to change in position. It's a concept that it's very common later, and there'll be these points where you will look back, okay, fine, Doppler effect. And Doppler shift is not just for sound, it's there in so many things. And also, more importantly, it is a very common source of questions in entrance examinations.
Exactly. And one interesting thing is scientists have found out the size of universe using this Doppler effect.
Exactly. As I told
Yeah.
you, this is simply because we are studying this in 11th grade does not mean it's not very important.
And this Doppler effect is applies to each and every wave, not just to our mechanical waves.
Right.
So let's see what this phenomena is. Suppose there is some relative motion between a source
Mhm.
which is generating sound
Okay.
and the observer who is detecting this sound. If there is some relative motion,
Right.
then you feel a different frequency other than the frequency sent by the source.
Right. So you feel a shift in the frequency.
Yeah.
And actually, human ears, you would remember, listening to sirens, blaring sirens, approaching and then leaving.
Exactly.
So you already know what Doppler effect is. Okay. We'll just mathematically model it here.
Exactly.
Okay.
So, by applying some basic concepts of relative motion and time period, you can arrive at this formula, and the derivation is available in most of the texts.
Right.
So, let's see how this formula physically supports this theory.
Right.
So, when suppose you have a siren here,
Okay.
and you are moving towards this siren.
Right.
From our experience, what we have observed was you hear siren with more frequency.
Right.
And take this formula,
Right.
V plus V naught
Okay.
by V, since Vs is 0, source
Right.
is stationary. This into the frequency of source.
Right.
So this ratio is obviously greater than 1.
Correct.
So that is what this formula says.
So what we're trying to show you here is an intuitive method to remember to how to use this formula.
Exactly.
When you have different directions of velocity and one of those things are moving, or both source and the receiver or the observer are moving. So we are trying to tell you how exactly to use the sign convention in this formula.
Yeah.
Okay.
So V dash is the apparent frequency, V is the frequency of the wave from the source,
Right.
and V, the capital V, is the velocity of wave in the medium. And V naught, as I have already shown, it's the velocity of the observer, and Vs is the velocity of the source. And the most important thing is, all these are with respect to ground frame of reference.
Right.
Like this will be encountered in problems. Please take a note of that.
Okay.
And you see plus or minus signs here.
Right.
So when you are moving towards the siren,
Right.
you hear more frequency.
Okay.
So I have put a plus sign here. So
Right.
effectively we can use a convention here, that is draw a line joining observer to the source.
Right.
Suppose this is the observer and this is the source.
Right. And if the length of that line is decreasing or increasing.
And draw a line from observer to the source.
Right.
If the velocities are in the direction of this vector,
Okay.
you take a positive sign.
Right.
If it is in the opposite direction, you take a negative sign. It's as simple as this.
Right. So we'll start with problems for the chapter waves, and the first one is here in front of us. It says y of xt is equal to 10 by 5 plus x minus 2t whole square, where xy are in meters and t is in seconds. Then we have to check which of the following are true, whether it's a pulse or it is moving in negative x direction, or whether the amplitude of the pulse is 2 meter, or if the velocity is 2 meter per second. So we are familiar with expressions for all these things and how to obtain them from y of xt. So let's work through it and find out how exactly it's done.
So let's start by recalling the properties of a pulse.
Right.
So a pulse doesn't change its form throughout its motion.
Correct.
So let's see how it is at t equal to 0.
Right.
So at t equal to 0, y of x comma 0
Okay.
turns out to be 10 by
Right.
5 plus x square.
Okay. Right.
So from this one can easily find out y max that at x equal to 0.
Okay.
So at t equal to 0 and x equal to 0,
Right.
we get y max
Okay.
as 2,
Right.
which is 2 meters because the dimensions are given in meters. So from this we can say that it is a pulse
Okay.
as well as the amplitude is 2 meters.
So we know it is a pulse because of exactly what reason?
Yeah. So if you plot this graph
Okay.
for time 0,
Right.
you get this graph in this way, which
Okay.
is symmetric about y-axis.
So we'll need to think about what the shape of that thing is.
Yeah.
And so are there more theoretical concepts you can verify from this formula, whether it's a pulse? Are there any more theoretical definitions apart from the graph?
This for me, this is the best way to go through because
Okay.
the functions are mostly in polynomial form or in exponential form.
Okay, so what is the essential condition for this expression to be representing a pulse?
Yeah, first one you can check if it is not tending to infinity, if x and t are
Okay,
going
so it has to have finite energy.
Yeah, it has to have finite energy.
Right.
And the second one is its form should not change.
Okay.
The form should be the same.
Okay.
So as time increases, this pulse will be moving on to right because omega and k have opposite signs.
Correct. The coefficients of x and t.
kx minus omega t, the form is kx minus omega t, they have opposite signs.
Correct.
So it is moving in positive x direction.
So B is obviously
So
wrong.
option B is wrong.
Correct.
And now for D option, to verify the D option, you have two ways.
Right.
We have one is a direct method. From the equation you can directly identify the value of omega to be 2 and the value of k as 1.
Okay, so basically omega is simply the coefficient of t.
Yeah.
And k is simply the coefficient of
x.
Correct.
So from here we have already studied that v is equal to nu lambda.
Okay.
So by substituting relevant expressions in the form of omega and k, we get it as omega by k,
Okay.
which is equal to 2 by
Right.
1, that is 2 meters per second.
Okay.
And there is another way to solve this also.
Right.
We have studied that Vp is equal to minus V into slope.
Right.
So
What exactly does this formula represent?
yeah, this was a formula which we got for velocity of a particle.
Right.
Vp was dou y by dou t
Correct.
is equal to, and we need V here.
Right.
This is the unknown.
Okay.
We know the value of we know the function y,
Okay.
and this is dou y by dou x.
Right.
So you can partial differentiate with respect to t and then with respect to x and then divide.
Okay.
So you get again V as 2 meters per second.
Okay. So this is the analytically correct
Exactly.
way of doing
But
this.
the shortcut is this.
Okay.
This
so,
would-
okay. So does this work even if the expression is fairly different from what new? For
Yeah.
example, here the function of x minus t, or omega t minus kx, actually it lies in the denominator.
Yeah.
But we are still sure that it will work, right?
Yeah.
Okay.
If it is in the form of exponential also it works.
Okay, so basically, no matter how the function is, if it is already in the form, of omega t minus kx, then we are sure that the coefficients of t, and x
And X will work.
will are omega and k.
Yeah.
Okay, so that's a very enlightening concept there, and honestly, that will save you a lot of time. And so this was problem 1. We were
So
asked
your D option is also right. So the correct answers are A,
B, A, C, and D. Okay, so we were asked to find out whatever we knew about this wave, actually about this expression, which we were not sure of what it is, and we determined that it was actually a pulse, and we did that through plotting it, and then discovering that it actually had finite energy and did not change with time, which is a very important property of a pulse. And then we saw that it was a function of the form omega t minus kx, which tells us that it was traveling in the positive x direction. So obviously option D was wrong. And then we found out the amplitude. How?
Yeah. Amplitude, you can differentiate the y value,
Okay.
dy by dx,
Okay.
and then you get the maximum value as 2
Okay.
for x equal to 0.
Okay. So
Or you can simply see this expression.
right.
For x from 0 to infinity, this is a decreasing function, and from 0 to minus infinity also it is a decreasing function.
Correct. So it has to
be maximum at x equal to 0.
So where it is 2.
Yeah.
Correct.
So the amplitude is 2.
Right. And finally, we came down to determining the velocity, which can simply be written as omega by k. And analytically, you can look at how we did it. We calculated v from partial differentiating the expression with respect to time and then respect to x.
Yeah.
And we can take its ratio, and from there we get minus v.
Yeah.
Okay. So this is how we can solve such problems. And again, this set of problems are pretty common in entrance examinations, because all people try to do in such questions is bend the expressions but now that no matter how much they can change the expression, these properties still hold. So this was problem 1. We'll look at the next one now. So moving on with problem 2, a rope of mass 1 kg and length 1 meter has a tension 10,000 newtons. It is tied to the end of a steel bar as shown here. A progressive wave y xt equals a sine kx minus omega t is generated at the free end of the rope. What we need to find out is the expression for the reflected and the transmitted waves, and we are given the density and Young's modulus of steel.
Yeah. So let's start by finding out the velocities of the wave in each of the medium.
Right.
Let's say that the rope is medium 1
Okay.
and steel bar is medium 2.
Right.
So V1 is equal to under root T by mu,
Correct.
which gives out V1 as 100 meters per second,
Right.
and then V2 is under root Y by rho.
Okay.
By substituting the values, we get it as 5000 meters per second.
Correct. So
From-
we start by calculating velocity.
The velocities,
So that we
yes.
can apply the formula for transmitted
To calculate
amplitude.
the amplitudes of the reflected and the transmitted wave.
Right.
So the formula for reflected waves amplitude is AI into under root V2 minus V1 by V2 plus V1,
Correct.
which turns out to be A into 4900 by 5100. So you get reflected waves amplitude as 49 A by 51. Similarly, apply the formula for A transmitted.
Right.
You get it as 100 A by 51.
Correct. If you
So-
remember, both of these we discussed in theory, and
Yeah.
we did mention that it was important for problem solving.
So now let's see how what happens. Since we got amplitude as positive,
Okay.
the reflected wave doesn't change the phase.
Right.
This is what we can infer from this.
Okay.
And transmitted wave obviously doesn't change the phase.
Right.
So the reflected wave travels in the negative x direction.
Correct.
So y reflected of x comma t
Hmm.
will be 49 A by
51. Correct.
into sine of kx plus omega t,
Right.
and y transmitted will obviously travel in positive x direction.
Right.
So it will be 100a by 51 sine of kx minus omega t.
Right.
So the important things to see here is the reflected wave doesn't change the phase.
Right.
It maintains its phase, and the transmitted wave always maintains a phase.
Okay. So here was problem 2. We were given a rope, and it was a composite system in which we had a rope and a steel bar, and we had to find the expressions for the transmitted and the reflected waves. So we start by calculating velocities and two media, and then we apply what we know to be correct about reflected and transmitted waves, and we get the expressions for their amplitudes. After that, we just have to check whether what directions they're traveling in, and we have to check whether the reflected wave has a phase change or not. Okay, so that was problem 2, and we'll move on to the next one now.